this video, we are going to discuss about current to voltage converter. So this current to voltage converter, it is also called as transistors amplifier. And it is also called as current controlled voltage source. CCVS. Thus, current that is V0, my output voltage is equal to K times the magnitude of the independent II. So I can write V0 is equal to KII. K is equal to V0 by II. So what is K? K is nothing but it is measured in terms of ohms, and it is also called as V by I is resistance. Okay. These CCVS is used whenever we want to measure a voltage. Okay. For example, whenever the output current is proportional to the instant light energy that is obtained from the photo devices like photocells and photodiode, and this output current from the photo devices can be converted into voltage by using the current to voltage converter. So here I am going to discuss the circuit diagram of this current to voltage converter with the help of inverting amplifier and also using the non-inverting amplifier. So we will obtain the output B0 that is equal to minus I into R. Okay, so that is I into K. And this minus is based on the direction of the current source which we are connecting. The current which we are connecting. Okay. So here let us discuss the circuit based on the inverting current to voltage converter. So this is an opamp, and you can see have connected R1, that is a feedback resistance. So in order to reduce the high frequency and possible oscillation, a capacitor CF can be connected across the RF also. Okay. So you can see since there is no current flowing through the opamp, I can write this current as II. Okay. So based on the concept of the virtual ground, I can make this one as 0, right? Since the positive terminal is connected to ground, this is also 0. So I can write 0 minus V0 is equal to IA into R1. So here my input current that should be greater than the input bias current. I mean, that's the only condition which we have to follow. So I can write V0 is equal to minus I1 IIR1. So V0 by IA is equal to minus R1. Okay. So if you change the direction of the current, you will get a positive value. So that's all about the current to voltage converter using inverting mode, inverting amplifier. Let us discuss non-inverting current to voltage converter. So next I'm going to connect the same circuit with the help of non-inverting circuit. Okay, so insert. So we know that VA is equal to, V naught is equal to VA into 1 plus RF divided by R1. Okay, since there is no current flowing inside the op-amp, the entire current will flow through this resistance. So I can write VA is equal to I1 into RI, right? IA into RI. So I will substitute it here, IA RI into 1 plus RF divided by R1. See, so this is a circuit which is showing the non-inverting current to voltage converter. So you can see the input current IA has return path to the ground, and the voltage at the non-inverting terminal V A is given by IA into RI. So the output voltage is this one. Okay. Next, let us discuss about current amplifier. So this is a circuit of the current amplifier. On the RL is your load, okay? Load resistance, this is here. And so from this I can write the current flowing through this one is, let me assume this is I2. Okay, so the current is, this one is IS. So here, since the load resistance is added to the circuit, I can write I2 is equal to V naught by RL. What is V naught? V naught, that is, the current is flowing in this direction. So V naught minus 0 is equal to IS R1. So V naught is equal to IS R1. So you substitute here, I2 is equal to IS R1 divided by RL. What is I2 divided by IS? This is my gain, right? Current gain. That is, I can write it as R1 by RL. So this is called as current amplifier. The circuit is called as current amplifier because the input is a current and the output is also a current. So if suppose R1 value is greater than RL means it's a current amplifier, right? Suppose if R1 value is less than RL means it is nothing but current attenuate. So the disadvantage of the circuit is the current gain and the current alternation is based on the resistance of R1 and R2. So R1 and RL, the RL is nothing but a load resistance. So if the load can be floating, then you can use this type of circuit, right? If I want floating load, I can connect so this is my IS and this is nothing but IL, and this one is nothing but I. So at this point IS is equal to IL plus I2, right? So what is my I2? I2 is nothing but
yeah, I need your everything.
From the previous circuit, I can write this I2 as from this equation, right? I2 as IS R1 divided by R2 here. Okay. Because here I have connected R2 resistance. Okay.
And got it.
Sorry. This is nothing but incoming current is IL and outgoing current is IS, right? So I can write IS is equal to 1 plus R1 by R2. So what is my IL by IS? IL by IS is equal to 1 plus R1 by R2. So here the load is nothing but floating. Okay. And you can see my output equation that is independent of the load resistance. Or okay.
When you build it, and then take it.
Here the signal current which produces the voltage drop, that is VR1 across this resistance R1, and the voltage at the junction of the three resistors, that is R1, R2 and RL, is nothing but VR1, because the opamp non-inverting input terminal remains at the ground level. Okay, so this is also VR1, this is also VR2. So the opamp output voltage has to be more positive than VR2. Right? This is VR2, but VR1 is equal to VR1. Yeah. So while designing, the sum of the voltage drop across this RL and R2 must not be so large that of the opamp output attempt to exceeds its maximum output voltage range.